All right, today we're going to take a look at section 6.2, which is addition and subtraction of rational numbers. And kind of just a word of observation. So fractions, I think somebody asked me last time, like, where do you kind of see fractions introduced in curriculum these days? Usually looking at end of 4th grade, 5th grade kind of area. You see them hit hard even through 6th grade because fractions are a concept that are difficult for students to do. The other thing that will often happen on curriculum is that oftentimes you'll actually encounter multiplication and division before you encounter addition and subtraction, which is obviously sort of backwards from the way that we do whole numbers, right? You know, you learn addition and subtraction in 1st and 2nd grade. You don't do multiplication until the end of 2nd or in 3rd. But multiplication and division is actually easier with fractions than addition and subtraction is. So as we're taking a look at that, your book still has it set up in this order, so I'm going to do it that way, but just kind of be aware that it doesn't always come this way in all the curriculum choices that are available these days. All right, so to start with, addition of rational numbers. I hope that you've printed these off. Yes? Some nodding. Okay, that's good. So with some addition of rational numbers, we have two possibilities. We could have denominators that are alike, or we could have denominators that are not like or unlike denominators. If you have like denominators, and you have a over b and c over b, and you add them together, then you get a plus c over b. It's not over b plus b. Okay? You add the numerators together, you don't add denominators. The denominator stays the same. And I can't remember if I had a picture later. I think I'll do it here. Just to kind of give you a sense of why that makes sense, think about a pizza, something we're all quite familiar with, right? I know you've eaten some pizzas in your day. Me too. And when we talk about a pizza, they're often divided into 8 slices. So I'm going to draw my picture like that. Okay? So if Kira eats 1/8, and Matthew comes along and he eats 1/8, then 1/8 and the 1/8 that they ate is a total of 2 out of the 8 slices of pizza, right? So real simple, straightforward example, but that's the way it works. We have 2 out of the 8 that we're talking about, and that's why we're adding the numerator and not adding the denominator, okay? The denominator is the number of total parts present in the whole object that we're taking. However, if our denominators are not the same, we've got to get them the same in order to be able to work with them. And so we talked last time about common denominators and least common denominators. In fact, you guys have asked some really good questions already today about finding those. And we need common denominators in order to add or subtract fractions. Absolutely have to be. So one way to do that is to find just simply any common denominator, and that's actually what you see happening on this definition is the two denominators are multiplied together over here, right? And then the numerators also have that happen. So I'm going to show you a couple of ways to think about that. Let me show you a visual one. For some of us super visual learners, I'm actually a really big visual learner myself. Is you can think about multiplying sort of across the fractions. So there's your a times d and your b times c, and then you're multiplying along the bottom. So it's a nice visual for this. If you think more algebraically in terms of like the why is this happening, you can think about multiplying fractions. So this is what I'm actually doing, right? I'm multiplying this first fraction by d over d. And I'm multiplying my second fraction by b over b. So that's an algebraic sort of sense of why that's happening. Whatever works for you, works for me. This isn't the only way to get common denominators, right? We could look for something they have in common that's smaller. And sometimes that saves us some steps later on if we happen to notice it. But, you know, when push comes to shove and you're not sure what else to do, this will always work. And that's always a nice tool to have, is something that works all the time. So we're going to do a couple of examples. On the first one, you notice they have what? Common denominators. So the denominator will stay the same. And what will my numerator be? It will be 6. And as we're working through fractions, we're always going to reduce when possible. So by reduce, I mean that the numerator and the denominator can't have any common factors, not necessarily that we're going to turn it into a mixed number. That's not what we're talking about. So on this one, 6 and 3 do in fact have what in common? A 3. So you don't necessarily have to write it like this, but literally that's what we're doing. We're dividing the numerator and denominator each by 3 to give me 2 over 1 or simply 2. Now if you can go from here to here on whatever problem you're working with, that's great, no problem, okay? But I would prefer that you didn't go from here to here, because if you do in fact make a mistake, I can't give you any partial credit because I don't really know where the mistake is being made, okay? All right, let's try another one. These don't have common denominators, right? No, they don't. So let's talk about this one from a visual sense. I'm going to multiply 1 times 3 to give me 3, plus 4 times 5 to give me 20, and then 4 times 3 to give me 12. I like the visual. I think it's cool. And especially when you're working with these kinds of values at the beginning, a lot of the denominators don't have anything in common. It's very, very often the case. And they're often quite small numbers to be dealing with, too. You're not dealing with denominators like you were in your last lesson where you had 5,400. Was that what you had, Brooke? I mean, like, that's huge, right? You don't usually start out with those kinds of fractions, right? You're dealing with smaller values. So if I simplify this, what will I have? 23 over 12. And do 23 and 12 have anything in common? No. So this is a perfectly valid answer. You don't need to turn it into a mixed number. Don't do more work than's necessary, okay? All right, so now that I've said you don't have to turn it into a mixed number, there are going to be times when they're going to ask you to. So let's take a look at that next. Mixed numbers. To be honest, mixed numbers are not very convenient to use in mathematical computations. However, they are very real-world kind of numbers. We use them all the time in everyday life to represent an integer combination with a proper fraction. So if I ask my daughter, how many pieces of pizza do you eat? She very well might say 1.5. And you would know exactly what that meant, right? But if she said 3 halves, you would look at her, she's like, she's a little weird. I would too. Be like, what? Why did we say 3 halves? It's the same number, but we don't talk like that, right? So in real world contexts, it makes a lot of sense to turn things into mixed numbers because we have a visual about what that is immediately. So when we're talking about turning numbers into mixed numbers, it's just division. Remember, that's what a fraction bar is. It represents division. So we're really taking 14 and dividing it by 3. The numerator goes underneath our division bar, and the denominator goes on the outside. So how many times will 3 go into 14? 4. 4 times 3 is 12, which gives me 2. So this number and the number I'm dividing by form the remaining fraction of 4 2/3. Okay. Work-wise, if you can go from here to here, especially when numbers are small, that's okay. That makes sense to me. I don't necessarily have to see the work that you're showing. As your numbers get larger, you're just going to have to show some work because you're going to need to do the work. You're not going to be able to do all of them in your head, of course. I wanted to show you this one for 2 reasons. Number one, because it's negative. And so there's this sense that somehow that changes something, and it really doesn't. And then also this is going the other direction. So we're taking a mixed number on this one, and we're trying to turn it back into an improper fraction. So first and foremost, the negative at the beginning, it doesn't get involved in any of the computations. It's just going to make my answer negative at the end. Okay? So try to ignore the negative while you're working. You don't need to work with it. We're really just focusing on the number 3 5/8. So let's start with the 3 5/8. So again, I like visual techniques because that's how I think. But I'll show you a couple of ways to think about this. Visually, what we're doing is we're multiplying 8 times 3, and then we're adding it to the 5. So 8 times 3 is 24, plus the 5 on top would be 29, right? So 29, and then the denominator stays the same. So let me show you like the why behind that, because it's great to see that it works like that, and a lot of kids are going to benefit from that. But there's some kid in your class who's going to say, but why does that work, Miss Knack? I don't understand, right? Yeah, you've had them in your classes before. Maybe you are one of them. That's okay if you are. But let me show you why that works. What you really have here is the number 3 over 1 and the number 5 over 8. And that's why when we say it, we say the word and. This is 3 and 5/8. So what we're doing is we're actually multiplying this numerator and the denominator by 8 so that they have a common denominator. And then we're adding the numerators together because now they have a common denominator. It's not really mysterious. We don't usually think about the fact that that's what we're doing, but we are. Sound good? Excellent. Oh, and then our final answer needs to have a negative on it. My bad, because we ignored the negative at the beginning. The answer is on the negative at the end. The answer is negative at the end. Okay, properties of addition. So one of our properties of addition is that there's an additive inverse. So for any rational number, a over b, there exists a unique rational number, negative a over b, such that when you add them together, you get back 0. And it works for every rational number. Another property of addition is the additive property of equality. We actually use this property every time we work with equations. You do it with whole numbers and integers and everything too, but it works for rational numbers as well. If a over b and c over d are rational numbers, and a over b is equal to c over d, the two quantities are the same, then if you add the same number, e over f, to both sides of the equation, the summation of the left is going to be equal to the summation on the right. So these two properties are kind of the big sticking points when we work with solving equations. We're going to solve an equation, and I want to show you two different ways to solve this. One method is going to deal with improper fractions, and another method is going to deal with mixed numbers. Improper fractions is the only way that I learned to do this when I was a student, and maybe it is for you too, I don't know. But there is more than one method, and I always think it's good that when I have more than one option to show you that I do, because kids don't all think the same. If you have a kid that's really struggling to understand one method, but you can show them something else that they can grasp and use well, it's worth your time to do so. So let me show you a couple of ways to do this. So no matter what happens, we need to move this to the other side. The goal is to get x alone, right? So in doing that, the starting point is the same for both my methods. I need to add 2.5 to each side. So I'd like to show you, this will be my improper fraction method. And in this method, I have x equals, and I have the 3 1/3 plus 2 1/2. And what I'm going to do is I'm going to change both numbers into improper fractions to start with. So if I change this into an improper fraction, I multiply, then I add. So 3 times 3 is, plus 1 is 10. So this is 10 thirds plus, and we'll do the same thing on the next one. 2 times 2 is 4 plus 1 is 5. So we have 5 halves. So I've got mixed numbers. I'm sorry, my mixed numbers turn into improper fractions. And then I can use a visual method if I like, or something else. I'm going to multiply. 10 times 2 is 20. Plus 3 times 5 is 15. And in the denominator, 3 times 2 is 6. So the result is 35 over 6. But if the question starts out in mixed numbers, then the answer must also be in mixed numbers. If the question starts out without them, it's perfectly fine to leave it. Okay? But we started with mixed numbers, so we're going to give our answer in mixed number form. So I need to take 35 and divide it by 6. So how many times will 6 go into 35? 5. Giving me a remainder of 5. This is 5 and 5 6. This is the only way I learned in school to do this problem. And of course it works, and it works every time, and that's great. The thing that's kind of maybe less friendly about this approach is that you often end up with larger numbers than the other one. I have a numerator here, it's 35, and depending on if my denominators especially had been even larger, my numbers would have been even bigger. The numbers get bigger quicker, okay? This is the mixed number approach. And I really like it, actually. So in this approach, I have my 3 1/3 plus 2 1/2. And what I do is that I recognize, kind of like I did over here, that 3 5/8 is 3 plus 5/8, right? That's what it really means. And I separate these to do that as well. 3 1/3 means 3 plus 1/3. And 2 1/2 means 2 plus 1/2. So I group the whole number parts together, and I group the fractional parts together. And the beauty of that is that my numbers stay smaller. So 3 plus 2 is already 5. And it's easier to add these two fractions together than the 10 over 3 and the 5 over 2, just because they're smaller numerators. So if I use that and I think visually again, I have 1 times 2 is 2, plus 3 times 1 is 3, over 3 times 2 is 6, and I have 5 and 5 6. And that's pretty friendly. Now, there is a chance that when you add those two fractions together, you get a number that's improper again, right? Like, what if I added this and I ended up getting 7 over 6 at the end? Well, then I'd have to change it, and I'd have to divide, and I'd find out that the answer, was 1 1/6, and this 1 would combine with the other 5, and so forth. So there may be more steps at the end. It depends on the fractions you're working with. But even so, it's easier to divide 7 by 6 than it is 35 by 6, because the numbers are still just smaller. So you do get that benefit. Alrighty. Subtraction. We're doing addition and subtraction, so now we're to subtraction. Subtraction of rational numbers. The definition of subtraction: if A over B and C over D are rational numbers, and we want to subtract them, A over B minus C over D will be the unique value E over F, such that A over B is equal to C over D plus E over F. I know not all of you have had number theory with me, but we talk about this definition of subtraction with whole numbers there. So let me just do it with whole numbers because you'll see it happen easier than if I use fractions. The reason that 5 minus 1 is 4 is because 5 is equal to 1 plus 4, right? There's this symbolic relationship that if I shift it over to the other side, it's an addition fact instead of a subtraction fact. Sometimes you'll see them called families, no, I don't call them factor families. They say something about families in their title. And so the same thing's true for fractions, right? So if this is equal to E over F, then if I shift the C over D to the other side, there has to be a symmetric argument with addition. Theorem 6.8 says if A over B and C over D are rational numbers, then subtraction is the same thing as addition of the negative. Okay, again, we saw a similar thing happen for those who took number theory when we use whole numbers and integers. Not anything any different. Okay, so just like with addition of fractions, there's two types of subtraction of fractions. We have subtraction with like denominators and subtraction with unlike denominators. So if the denominators are alike, then we simply subtract across the top, right? So if I bring in the pizza and there's already one piece eaten, and so there's 7/8 of the pizza, and then I eat 3/8 of the pizza, 7/8 minus 3/8 is 4/8 is what's left, right? Same thing, we just subtract across the top. And then if the denominators are not the same, we actually have the same beautiful sort of picture that we had with the addition, where I can cross multiply and across the bottom and do the same thing and get common denominators that way. So really good stuff since addition and subtraction are so similar. All right, so you're ready to do a more complicated problem with some mixed numbers, because that's where we're headed. Started off with a fairly simple one, where we could do the two approaches, one with improper fractions and one with mixed numbers. And there may have been some of you who were thinking, and there's virtually little difference. They both take about the number of steps, same number of steps. Really, why does it matter? What benefit really does one have over the other? So I wanted to do an example where it is more complicated so that you can kind of see some of the differences when you have messier numbers. This is also how measurements are actually done when people buy fabric. I don't know if you've ever bought fabric before, but it is one of those things where they measure by the yard. And so Martine, in this problem, bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8 yards, pants using 2 3/8 yards, and a vest using 1 2/3 yards. How much fabric will be left over? So we first need to figure out what we're actually going to compute, and then we're going to compute it in two different ways. So what is this problem asking us to do with all these numbers? Can somebody tell me a word, like a sentence? Tell me in words out loud so that I can write it down as a numerical sentence. What am I going to do? Not equals, because that's not how the question asks it at the end. Okay, is that okay? Now, there's two ways to do this. You could do it exactly like what Summer said, and that's how I think about it too, because I'm just sort of like laying out my fabric, and I cut off the first piece, and I cut off the second piece, and I cut off, like literally that's what I would do if I were doing this project. Another way that you could do the problem in terms of mathematics is that you could do your 8 3/4, and you could add together everything you're subtracting, which would be totally fine as well. In other words, you're going to add up all the projects and then take them away from the total amount. So if you think about it like that, the problem just starts out a little bit differently. Your choice. Sorry, these are added then. 2/3. Okay? So it doesn't matter really which one we do. I think it might be a little bit easier to do the second one, maybe. So which one would you guys like to do? It doesn't really matter to me. Number 2? All right. So I will just change this over here. I'm sorry, that's not the one I want to change. These are. All right, so let's first do the method where we have improper fractions, okay? Just because that's the order I did the last ones in. So to do improper fractions, I need to get all of them in improper form. So I'll do all of them at the same time. I have 4 times 8 is 32, plus my 3 on top is, so 35 over 4. And then inside my parentheses, I have 8 times 1, 8, plus 7 would be 15, so 15 over 8, plus, and we do the same thing, 8 times 2 is 16, plus 3 is 19 over 8. And the last one, 3 times 1 is 3, plus 2 is 5 over 3. Okay, so 2 of them already match, right? So can we just combine those without going much further? Yeah, sure. So this is a 35 over 4. And then what's 15 plus 19? $34. So 34 over 8 plus 5 over 3. I need a common denominator, and I've got a 4 and an 8 and a 3. If you want, you can multiply them all together. It's okay. But actually, since the 4 and the 8 have 4 in common, multiplying the 3 and the 8 together will be sufficient. So if I take this one and I cross like that. Okay, somebody help me out with the calculator. What is 34 times 3? 102. Plus, what's 8 times 5? 40 over 24. And I don't really want my denominator to get any bigger, so I'm just going to use the multiplication of 6 on the first one to get the same 24 there. So, ooh, goodness, still, what is 35 times 6, sorry, 35 times 6? 210? Awesome. So, what is 102 plus 40? Yep, 142. So now I have 210 minus 142. And what is 210 minus 142? 68. So now I have 68 over 24. Fabulous. Got to divide that, right? You could flat out go to division right here, and that would be okay. But I think it might be easier to recognize, first of all, that they're both even. So I would probably start by dividing by 2 before we go any further. If you can get the fraction smaller, it's easier to do the division with it as well. So what's 68 divided by 2?
It'll divide by 4.
Oh, you want to do it by 4? Okay. If you happen to notice something bigger, by all means, holler it out at me. What's 68 divided by 4? 17. And 24 divided by 4 is 6. Maybe you can do that one then in your head even. Maybe, maybe not. How many times will 6 go into 17? 2, giving me a remainder of 5. So this is 2 and 5/8. It is a word problem. 5/6, sorry, thank you. Yards was what I was getting to. Yes, with yards is my answer. So do you get a better sense on this problem of how big the fractions get when we do improper fractions? They do, and that makes it kind of tricky to work with. Not impossible. It's not something you can't handle. It's not something your students can't handle. But it's not as easy as that first problem because the numbers are just bigger. And the reality is that at the point when you're teaching this to children, they're doing all the multiplication by hand. They're not using calculators still at this point, right? Yeah, not usually anyway. So let's take a look at another approach just so that you can see by comparison. This is the mixed number approach. So the problem, of course, starts out the same. I still have 8 and 3/4. Actually, no, I'm not even going to, well, I'll rewrite it. I was trying to decide if I want to rewrite it again. I have minus, and then I have 1 and 7/8 plus 2 and 3/8 plus 1 and 2/3. Okay, so I can group all the whole numbers together, and I can group all the fractions together. And in this approach, probably does go ahead and make sense to distribute that negative through so that I can group them more conveniently. So in particular, I have 8 minus the 1 minus the 2 minus the 1, all the whole number parts, plus, and then I have 3/4 minus the 7/8 minus the 3/8 and minus the 2/3. So far, so good?
Wait, sorry. Why do you have 8 minus 1 minus 2? Just move that, the negative sign in with each.
Yep. Yeah, I'm subtracting all the quantities inside, so all those quantities inside are negative already, and I'm just moving them to be grouped together. 8 minus 1 minus 2 minus 1, 4. And inside of this over here, again, this happened before, we have like denominators on a couple of them. Whoops. Here and here. So it would kind of be nice to go ahead and combine those as well. So I have 3/4, and then what is 7/8 and 3/8? They're both the same sign, so we just add the numbers together. It's 10/8, and the sign's negative, so it's minus 10/8. And I have minus 2/3. We could deal with the fraction denominators where they are, and it would be okay. We also could see that 10 and 8 have something in common and make the fractions smaller. And smaller fractions are easier to work with, so I'm a fan of making things smaller. Because 10 and 8 will reduce to what? What is it? 5/4. So I have 3/4 minus 5/4 minus 2/3. So again, two of them match. So what is 3/4 minus 5/4? Yeah, it's negative, because the 5/4 is bigger, to negative 2/4 minus 2/3. Is there one that can get simpler? Yes, indeed. That's minus 1/2. So I have negative 1/2, and I have negative 2/3. So there's no reducing anymore on that point. So we can find a common denominator. They're both negative. Everybody sees that, right? So this is a negative and this is a negative. So when I multiply the negative, and you can, the easiest way to sort of remember this is we did this last time, although you may not have recognized it, is that the negative can group with the top numbers, not with the bottom. You got to pick somewhere, so you might as well pick the top. So it's negative 1 on top times the 3, so that it's negative 3. And it's a negative 2 on the top times the 2, so it's minus 4. Negative 3, negative 4 would be what? Yeah, so now I have 4, and I have negative 7/6. And as far as sort of reducing the whole number parts and reducing the mixed number, or the fractional parts, we're simplified, right? Now I have to combine them back together to get a mixed number. The problem, of course, is that 7/6 is improper. What would the mixed number version of 7/6 be? 1 and 1/6. So this is 4 minus 1 and 1/6. And do you see a 4 and a 1 that could again be combined? Yep. So this becomes 3 and 1/6. Nope, something's wrong. What did I do wrong?
You need a minus.
Oh, because it's a minus 1/6. 3 and then minus 1/6. That's what I wanted to do. There we go. Okay, so this is a little trickier. It's a little weird. I still have to subtract, right? I mean, and I really do. I have to subtract this value. So what do? There's a couple of different things that you could think of. One thing that you could think of is the fact that this 3 could be separated as a 2 and a 1. So here's my 2. And then 1 is the same thing as 6/6. So if I have 6/6 minus my 1/6, there's my 5/6. So yay for the fact that I didn't have as big of fractions. Not so yay for the fact that at the end I had to subtract a whole number part and a fractional part, and that's weird and awkward. There's not like a strong contender for who's the best option here. It's just going to depend on the kid and which way they think better. But there's 2 different ways to do it. All right, so we only have like 2 more problems to do, but I want to stop right here anyway, because we only have like 1 more minute of class. So we will pick up with this last little bit of this section on Monday, and do group work on Monday, and we will also attempt to cover most, if not all, of section 6. Well, is that right? Anyway, we're supposed to start section 6.3 on Monday. Yeah, we'll start 6.3 on Monday and we'll finish it on Wednesday, okay? So we'll finish this part and the group work on Monday, and then they'll start the homework after that. So there's no homework for the weekend. Just set this aside in your folder and enjoy yourselves, and I'll see you guys on Monday.